Hi everyone, I'm Hussein. We will talk about parallel processing today. Let's start. We are going to talk about parallel processing and some of the main types of architecture used in this field. Let's go through them one by one. First, we have symmetric multiprocessor or SMP. These systems have multiple processors that share the same memory. They also keep their cache coherence, which basically means the processor can together smoothly without messing up data. Next, multi-threaded processor. Here, a single CPU can handle multiple threads at the same time. This helps make the CPU work more efficiently and keeps things running faster. Then chip multiprocessor. These are multiple cores packed into a single chip. It's like having a small team inside one processor. Another type is cluster. This is basically a group of separate computers connected together to act like one big system. Clusters are great for really big tasks or heavy computation. We also have NUMA, which stands for Non-Uniform Memory Access. In NUMA systems, memory access depends on where the data is located. Example, some data is closer, some is further away, but the system manages it to stay efficiently. And finally, vector computation, which you often see in supercomputers. These systems are designed to do huge amounts of math really quickly, which is perfect for scientific simulation or data-heavy tasks. Now, Firin's taxonomy, which classifies computer architecture based on number of instructions and data streams they can handle simultaneously. First, we have single instruction and single data. This is classical, traditional step where one instruction is executed on one piece of data at a time. It's simple and single core processor model. Now we move on to single instruction and multiple data. Here, a single instruction is applied to multiple pieces of data at once, which is common in vector processing and tasks like graphical rendering. Next, multiple instruction and single data. This is quite rare, but it involves multiple instructions working on a single piece of data, often seen in specialization systems like fault-tolerant computing. Finally, multiple instruction and multiple data, which is used systems like SMP, cluster, and NOMA. In this architecture, multiple processors can execute different instructions on different pieces of data at the same time, allowing for high scalability and parallel computing. These slides show the main types of multiple processor organization based on how instruction and data are handled. First, we have SISD, which represents the traditional single processor system. One control unit sent one instruction stream to single processing unit working on one data stream. This is classical sequential computing model. Next, SIMD. In this organization, a single control unit broadcasts the same instruction to multiple processing units. Each processor works on different data at the same time. This model is widely used in applications such as image processing, graphics, and machine learning. Finally, we see MIMD system. Here, multiple processors execute different instructions on different data stream. MIMD can be implemented with either shared memory or distributed memory, and it's the most flexible and powerful model for general-purpose parallel computing. Overall, this classification helps us understand how parallel systems are designed and where they are best applied. What we see here is symmetric multiprocessor system. In simple terms, SMP refers to a computer architecture in which two or more processors of similar capability work together while sharing the same main memory and resources. Each processor has approximately the same access time to memory and can perform the same function, which is why this system is called symmetric. Multiple processors with comparable performance. A shared main memory that all processors can access equally. Shared device either through common channel or through separate channel that lead to same device. An internal interconnection mechanism such as a system bus that links processor, memory, and input and output components. A crucial element of SMP system is the integrated operating system. The operating system coordinates all processors and manages their interaction at different levels, including job, task, file, and even individual data elements. It is responsible for processing, scheduling, synchronizations, and efficient resource sharing across the processor. Symmetric multiprocessor has some potential advantages. Firstly, performance. If tasks are well organized, some of them can be executed in parallel, resulting in better performance than a single processor system of the same time. Second, availability. If one processor fails or stops, the remaining processor can continue to operate. This may cause a slight performance degradation, but the system does not fail completely. And then incremental growth. The system can be expanded by adding additional processors. Last advantage is scalability. It becomes possible to offer processors with different performance level and different cost according to user requirements. These characteristics are closely related to how efficiently the operating system utilizes the available processor. Finally, in SMP system, the user experiences the systems as if it were a single processor machine, while the operating system manages multiple processors transparently. Now, take a look at SMP organization. Each processor may contain a control unit, an arithmetic logarithmic unit, register, and one or more cache memories. Through the interconnection structure, processor can communicate with memory and input and output units. A single shared main memory is used in the system. In some systems, each processor may have its own private memory. As shown in the figure a bus structure is used for system communication. This symmetric multiprocessor organization illustrated in the previous figure is built using a bus-based architecture. When a single processor system is used, the bus architecture provides addressing and arbitration and time sharing. In a symmetric multiprocessor system, it additionally provides simplicity, flexibility, and reliability. The weak point of this organization is performance, since the data transfer rate depends on clock speed. To overcome this problem, a tree-level cache hierarchy is used. However, this introduces the cache coherence problem. In multiprocessor systems, when a user designs a program, they do not need to worry about whether the instruction or thread will be executed on single processor or multiple processors. This responsibility is handled by operating system. However, in order for operating system to perform this task efficiently, it must consider several important factors. Firstly, simultaneous concurrent process. The operating system must allow multiple processors to run the same operating system code at the same time safely. And scheduling. The OS must assign ready process to available processor without conflicts. And, and then synchronization. The operating system must control access to shared memory and input and output resources, memory management, the consistency across all processors, reliability and fault tolerance. The system should continue working even if one processor fails. In bus-based architecture, to overcome the limitation imposed by system clock span and to execute instructional thread more efficiently, processors are equipped with a tree-level cache hierarchy. However, this design can lead to a situation where the same data is stored in multiple caches with different values during the write operation. This problem is known as cache coherence. There are two main write policies, write back and write through. In write back policies, when a write occurs, only the cache is updated and main memory is updated later. When the cache line is awaited or requested by another processor. This improves performance but makes coherence management more complex. In write-through policy, write operation update both the cache and main memory at the same time. This approach is safer but slower due to increased memory traffic. Even with write-through, coherence problem can still occur if other cache holding the same data are not properly updated. Cache coherence solution can be divided into two categories, software and hardware. In software-based cache coherence approach, cache usage is restricted and coherence issues are shifted from runtime to compile time. Although this reduced hardware complexity, it increased the burden of compiler and operating system and generally result in less efficient cache utilization. In hardware-based solutions, snooping and directory-based approach are used to track write operation across cache. This approach defines how memory updates are detected and propagated. The Messiah protocol is widely used coherence protocol that specifies the action to be taken by cache by defining state transition for cache line. This concept will be examined in more detail in following slide. Snoopy protocols are preferred in small bus-based systems where all cache can listen to the same bus, while directory-based protocols are used in large systems with complex interconnection. In directory-based systems, a central controller in main memory tracks data ownership and sends targeted updates, whereas Snoopy systems rely on broadcast over a shared bus. In terms of failure, Snoopy systems depend heavily on the bus, while a directory-based system may suffer from a central control bottleneck. Message protocol use 2-bit per cache line to represent 4 states: modified, exclusive, shared, and invalid, each describing whether the data is up-to-date, shared, or usable. Basic protocol there are 4 cache line states: modified, exclusive, shared, and invalid. Transition between these states depend on whether a read or write operation occurs and whether that operation results in a hit or a miss. Read hits and write hits usually completed immediately because the data is already present in the cache and cache coherence is not violated. If necessary, the snooping mechanism ensures that other caches are aware of the operation. In the miss situation, the cache line state may change depending on whether another processor holds a copy of data and whether the copy has been modified. The message protocol, together with Snoopy-based coherence, is typically designed for L2 cache, which are connected to a shared bus. However, in some architecture, the protocol can be extended down to L1 cache level. Next system is multithreading and chip multiprocessor. Processor performance is mainly determined by clock frequency and number of instructions completed per cycle. To improve performance, designers increase clock spend or IPG using techniques like pipelink and superscalar architecture. However, this solution increases hardware complexity and power consumption, and they are reaching practical limits. Because of this, a different idea emerged. Instead of executing more instructions from a single instruction stream, we divide the work into multiple threads and execute them in parallel. This approach is called multithreading. To understand multithreading, we first need to distinguish between a process and a thread. A process owns resources such as memory and files, and switching between processes is expensive. A thread, on the other hand, is a small execution unit of execution inside a process. Threads share resources but have their own execution context, so switching between threads is much cheaper and faster. Thread can be managed in different ways. User-level threads are managed by application, while kernel-level threads are managed by operating system and can run on multiple processors. Thread can also be classified as explicit or implicit. Explicit threads are created by a programmer on operating system, which is the most common approach today. Implicit threads are automatically extracted by the compiler or hardware from a single program to increase parallelism without programmer involvement. In summary, multithreaded improves performance by increasing parallel execution while avoiding the complexity and power cost or more aggressive hardware design. In the multi-threading and chip processor system, there are 4 different type system. Firstly, a single-threaded, the processor runs only one thread at a time, so there is no parallelism. In Figure A, we see an example of single-threaded if there is a wait processor stay idle and there is no parallelism. Intervaled multi-threading thread take turn each clock cycle so the processor can execute instructions from different threads alternatively. In figure E, the thread changes every instruction circle. This way the processor does not stay idle. Third method, blocking, blocked multithreading. A thread runs until it hits a latency, like memory delay. Then another thread takes over. This may cause a clock cycle when switching. Figure F, a thread runs until it occurs a latency, and then the thread is switched with a loss of one instruction circle. Third one, simultaneous multithreading (SMT). The processor can execute instructions from multiple threads at the same time, sharing its execution units. And last one, chip multiprocessor multicore. Multiple processor core are on same chip, so many threads can run truly in parallel, combining multi-threading and multi-core parallelism. For example, a multi-threading system, Pentium 4. Some newer Pentium 4 models are used multi-threading technique called hyper-threading. Essentially, it is SMT supporting two threads, so one processor acts like two logical processors. IBM Power 5. The Power 5 combined chip multiprocessor with SMT. The chip has two separate processors and each processor supports two threads simultaneously. Simulation show that two-way SMT processor perform better than a single four-way SMT processor because extra thread can cause cache thrashing. Instruction flow of each thread has its own program counter and some dedicated resources, but they share the instruction cache and translation units. Instructions are fetched alternatively, decoded in parallel, renamed to physical register, and then issued to execution unit. This combination of SMT and multicore allows high parallelism and efficiently use of CPU resources. Now I will talk about an important and relatively recent development in computer system design, which is clustering. Clustering is an alternative to symmetric multiprocessor, especially for the server-based system, where high performance and high availability are critical. Unlike SMT, where multiple processors share the same memory, clustering is based on multiple independent computers working together. This is the difference about these two systems. A cluster is defined as a group of interconnected whole computers, also called nodes, that cooperate to act as a single unified computer resource. Each node is a complete system that can operate independently even outside the cluster. One of the key strengths of cluster is that it provides the illusion of single powerful machine while internally distributing our workload across many nodes. Cluster system offers four major benefits. The first is absolute scalability. A cluster can consist of tens, hundreds, or even thousands of machines. Each node may itself be a multiprocessor system, allowing cluster to far exceed the computing power of even the largest only big computer. The second benefit is incremental scalability. Cluster can grow gradually. New nodes can be added in small increments, which allows organization to start with a model system and expand it over time without replacing the entire infrastructure. The third benefit is high availability. Since each node is an independent computer, the failure of one node does not result in total system failure. The final benefit, superior to performance ratio. By using commodity hardware components, cluster can achieve equivalent, even greater performance than a single large machine, but at significantly lower cost. In summary, clustering is a powerful and cost-effective architecture that is especially well suited for modern server environment requiring scalability, reliability, and high performance. These slides summarize the main clustering method along with their benefits and limitations. First, passive standby. In this approach, one server performs all processing while a secondary server remains idle and only takes over if the primary fails. It is easy to implement, but it is costly and inefficient because the secondary server is not used for normal processing. It improves availability but not performance. Second, active secondary. Here, the secondary server also participates in processing tasks. This reduces cost and improves resource utilization. However, it increased system complexity since multiple active servers must be coordinated. Separate servers model use servers with their own local disk and no disk sharing. Data is continuously replicated to allow failover. This approach provides high availability, but the constant data copying creates high network and server overhead. In the server connected to disk approach, servers are connected to same disk system, but each server owns specific disk volume. If a server fails, its disks are taken over by another server. This reduces network overlap but usually requires disk mirroring to handle disk failure. Finally, server shared disk, also known as shared disk approach, multiple servers access the same disk simultaneously. This method has low network overhead and reduced downtime risk, but it requires low log management software to control concurrent, concurrent data access. In summary, each clustering method represents a trade-off between performance, availability, complexity, and cost. The best choice depends on the system requirement and workload characteristics. And these slides summarize the key operating system function required to fully exploit a cluster. First, failure management. Cluster can be designed for high availability or full fault tolerance. In highly availability cluster, ongoing requests may be lost during a failure, but new requests are redirected to another node. Fault-tolerant clusters go further by ensuring continuous access through redundant disk and transaction recovery mechanism. Failover transfer application to another node while failback restore them after repair. Second, load balancing. The cluster operating system must distribute work evenly across all available nodes. When new computers are added, they should automatically be included in scheduling. Finally, parallelizing computing. Some applications must run in parallel to fully benefit from cluster. This can be achieved using parallelizing compiler, explicit parallel application, or parametric computing, where some program runs multiple times with different parameters. Together, these mechanisms enable cluster to deliver scalability, performance, and high availability. Now, we will look at cluster and SMP together. Both approaches use multiple processors to support high demand applications and are widely available commercially. This main advantage of SMP system is that they are easier to manage and configure. SMP is very close to traditional single processing model, so most applications can run with minimal change. Typically, only the operating system scheduler need to be modified. In addition, SMP systems usually require less physical space and consume less power than comparable clusters. They are also well-established and stable technology. However, in the long term, clusters are likely to dominate high-performance server environments. Clusters provide far better incremental and absolute scalability, allowing systems to grow easily by adding new nodes. They also offer superior availability since system components can be made highly redundant. In summary, SMP systems are similar and efficient for smaller environments, while clusters are better suited for large-scale, high-availability systems. A new topic. The main architecture used in multiprocessor systems: UMA, NUMA, CC-NUMA, and cluster. First, UMA, or Uniform Memory Access, is the simplest model. All processors share the same memory and they all access it at the same time. This is what we typically see in SMP system. From a programmer point of view, it feels very close to a single processor machine. As systems grow larger, this model doesn't scale very well. That's where NUMA comes in. In a NUMA system, processors still share a single address space, but memory is physically distributed. So, accessing local memory is fast, while accessing memory attached to another processor is slower. CC-NUMA take this one step further by keeping the cache coherent using hardware support. Even though memory access times are different, the systems still behave like a true shared memory machine. Clusters are totally different. A cluster is made up of independent computers, each with its own memory. There is no hardware shared memory. Any sharing happens through the network, shared disk, and software layer. So, to summarize, UMA, NUMA, and CC-NUMA rely on hardware-based shared memory, while clusters rely on communication over a network. That's why CC-NUMA is much closer to SMP than to a cluster. Now, why NUMA was introduced? In SMP systems, all processors share a single main memory and a common bus. This works well for small systems, but as we add more and more processors, the shared bus becomes overloaded. Memory access traffic increased and cache coherence message and even more pressure. In practice, this limits SMP system to around 16 to 64 processors. Clusters were developed to overcome this limitation since each node has its own private memory. However, clusters are not private, a true global shared memory model, and much of the coordination is handled in software. NUMA was introduced as a compromise between these two approaches. It allows the system to scale to a much larger number of processors while still presenting a single shared address space to application. By distributing memory across multiple nodes and avoiding a single shared bus, NUMA achieves better scalability without losing the shared memory programming model. This figure shows how a typical NUMA system is organized. This system is built from several nodes, and you can think of each node as a small SMP machine. Each node has multiple processors, their own cache, and a partition of main memory. All of these nodes are connected using high-speed network. Even though the memory is physically spread across different nodes, the system still presents a single shared address space. So, for the processor, it looks like there is just one big memory. When a processor needs some data, everything happens automatically. If the data is already in cache, it is used right now. If not, the system checks the local memory first. If the data is local, it's fetched quickly. If the data is stored in another node, the request is sent over the network, the data is brought back, and then placed into local cache. So, main idea of NUMA is to scale up to many processor while still behaving like a shared main memory system without forcing the programming to deal with all this complexity. And then advantages and disadvantages of NUMA. So the main advantage is scalability. Compared to SMP, CC NUMA can handle many more processors while still keeping the shared memory model. Because the system is divided in nodes, each node has its own bus, so traffic stays under control. Performance mainly depends on how memory is accessed. If most data is local, performance is very good. Cache plays a big role here, and in many applications, good locality means remote memory access is limited. Operating system can also improve performance by moving frequently used pages closer to where they are needed. On the downside, is NUMA is not a drop-in replacement for SMP. Some changes are needed, especially at the operating system level, such as memory placement and load balancing. Availability can also be more complex and depend on specific system design. Overall, CC NUMA offers a good balance between scalability and performance, but it requires more careful system management. Now, last type of parallel processing, the vector computing is an approach that focuses on the data level parallelism. Instead of operating on single data element at a time, vector processors work on entire array or vector using a single instruction. This makes them especially powerful for applications such as scientific simulation, matrix operation, and signal processing, where the same operation is applied repeatedly to a large dataset. And a vector processor includes special vector registers that can hold many data elements at once. Vector instructions operate on these registers, allowing the same operation to be applied across all elements. These systems rely heavily on pipeline to achieving high throughput. Because large amounts of data are moved at once, memory bandwidth plays a critical role in overall performance. And advantages and limitations and modern use of vector computing. The vector computing offers excellent performance when applications have regular data access patterns and can be easily vectorized. However, it performs poorly with irregular data structure or complex control flow. While classic vector supercomputers are rare today, the core idea lives on in modern technology such as SIMD instruction and GPU and vector extension in CPU. And that's all. Thank you for listening.